Hi, in this video we are going to study the Fourier series representation of a periodic real valued signal, or rather the conditions that should be satisfied by the Fourier coefficients in the Fourier series representation of a periodic real valued signal. Now, remember that if we have an arbitrary periodic signal, we have a Fourier series representation, and this representation is valid for real valued or complex valued periodic signals. So, let us start with a certain signal. Let x of t be a periodic signal, and the fundamental period is equal to t0. Okay, this is the fundamental period. So x of t has the Fourier series representation k from minus infinity to plus infinity, ak e to j k omega 0 t. Here omega 0 is related to t0 by means of this relation 2 pi over t0. Now at the moment we do not specify anything about x of t. It can be real valued or complex valued. Now, let us try to obtain the Fourier series representation of the conjugate of x of t. Now, x star of t, the complex conjugate of x of t, is also periodic with the same fundamental period. Same fundamental period, capital T0. Therefore, x conjugate of t will have a Fourier series representation. Let us call the Fourier coefficients pk e to j k omega 0 t, k running from minus infinity to plus infinity. So how can we evaluate the Fourier series coefficients pk in terms of ak, the Fourier series coefficients of x of t? Let us try to answer this question. Now we can start with the Fourier series representation of x of t, and we can, okay, so our problem is to evaluate bk in terms of ak's. So we can start with the conjugate, complex conjugate of x of t by evaluating the complex conjugate of the Fourier series representation, ak e to jk omega 0 t. Okay, we take the conjugate of this Fourier series representation. Now, conjugation, complex conjugation operation can be performed term by term. So, x complex conjugate of x of t is k running from minus infinity to plus infinity, ak complex conjugate, the complex conjugate of the coefficients, and e to j k omega 0 t complex conjugate. But the complex conjugate of the complex exponential is simply e to minus jk omega 0 t. Okay, now how can we continue after this step? Now, we see a series expression in terms of these complex exponentials with a negative sign in the exponent. So we have to get rid of that negative sign. So let us change the index as follows. Let m be minus k. So x complex conjugate of x of t will be expressed as a minus m complex conjugate e to j m omega 0 t. And m is running from, now when k is tending to minus infinity, m tends to plus infinity. So from plus infinity to minus infinity. But in the series expression, in fact, the order can be changed. And also, m is dummy, so it's a dummy index. Change it to k. So x conjugate of t is equal to, and we can change the order, k from minus infinity to plus infinity, a minus k conjugate e to j k omega 0 t. So we now see that this is in the form of a Fourier series because we have a Fourier series expression in terms of the superposition of the complex exponential functions e to j k omega 0 t, and the coefficients are given by means of this expression. Therefore, bk, the Fourier series coefficients of x of t conjugate of x of t is related to the coefficients of the original signal x of t by means of this relation. Okay, so if we know the Fourier series coefficients of x of t, we can calculate the Fourier series coefficients of the complex conjugate of x of t by means of this relation. Now, if x of t is real valued, complex conjugate of x of t is equal to itself. Therefore, bk's will be equal to ak's, and we will have a certain relationship satisfied by the coefficients of the Fourier series coefficients of the real valued signal. So our next concept to be discussed is this point. Okay, now to summarize the result we have just obtained, if x of t is a periodic signal with Fourier series coefficients ak, then the complex conjugate of x of t will have the Fourier series coefficients a minus k conjugate. Okay? Now, let us now consider the case of real value signals. Now, let x of t be real valued. Then, the Fourier series coefficients of x of t will satisfy the following relation. Ak will be equal to A minus k complex conjugate. Why? Because since x of t is real valued, now in fact the straightforward proof of this fact is as follows. Since x of t is real valued, x of t is equal to x conjugate of x of t complex conjugate. And therefore their Fourier series coefficients must be equal to each other. So for real valued signals, we have this property. Now, we can write down the same expression in the following form. Now, AK equal to A minus K complex conjugate. If you take the conjugate one more time, we get A minus K equal to AK conjugate. Now, this is a more informative form of the same expression. In fact, it tells us the following. For real valued periodic signals, the Fourier coefficients with negative indices can be obtained from the Fourier series coefficients with positive indices by means of this expression. Well, another interpretation of this result is as follows. Here we easily see the following. Now, the positive index k corresponds to the frequency k omega 0 in the complex exponential signal. And similarly, minus k corresponds to minus k omega 0. So we have the positive and negative frequency concepts. So we interpret this result as follows. In the Fourier series representation of real value signals, whatever you have at a positive frequency, you have a counterpart at the corresponding negative frequency, given by means of this relation. Now, a very straightforward example, in fact, a trivial example, is as follows. X of t equal to cosine omega 0 t. This is obviously a real valued periodic signal. Real valued, and it is periodic with the fundamental period t0 is equal to 2 pi over omega 0. But we also know that cosine omega 0 t can be written as 1 over 2 e to j omega 0 t plus 1 over 2 e to minus j omega 0 t. So, cosine omega 0 t has this Fourier series representation, which is a finite sum composed of only two terms. And we see that we have a positive frequency component at omega 0 and a negative frequency component at minus omega 0. And the coefficients are 1 over 2 for both cases. Another example may be sine omega 0 t, which is again a periodic signal which is real valued. Therefore, it should satisfy the Fourier series coefficients must satisfy the relation we have just obtained. So sine omega 0 t can be written as 1 over 2j e to j omega 0 t minus 1 over 2j e to minus j omega 0 t. Now again, we see that we have two frequency components, omega 0 and minus omega 0. The complex exponential functions have those frequencies, the positive frequency and negative frequency, and the coefficients also satisfy the condition we have just obtained. Therefore, in the representation of real valued periodic signals, we have the so-called, in the literature, this relationship is called the symmetry relation. The relationship between the coefficients in the Fourier series representation corresponding to positive frequencies and negative frequencies. Okay, another example is our periodic pulse train. Let us remember that example. We have a pulse, rectangular pulse with magnitude A over the interval from minus t cap over 2 to t cap over 2, and the magnitude is equal to A. Then we have the periodic extension of this pulse as n from minus infinity to plus infinity, p of t minus m t0. Here we can choose t0 greater than t cap, which is the duration of this pulse, just to avoid overlaps. So we have a neat looking periodic signal. Okay, so x of t has the Fourier series coefficients given by ak, which is we have already calculated as a t cap over t0 sinc k t cap over t0, or in terms of the expression of the sinc function, a t cap over t0 sine k pi t cap over t0 divided by k pi t cap over t0. Now, obviously, in this case, the condition is satisfied, but here the coefficients turned out to be also real valued. Now, in a minute, we are going to see why this is the case. But obviously, a minus k is equal to ak conjugate, but ak is real valued, so a minus k is equal to ak in this case. So a minus k turns out to be equal to ak in this case. So we have this property. Now, if we look at the previous example, in cosine omega 0 t, we have obtained coefficients in the Fourier series representation, which is composed of only two terms, as 1 over 2. Both components have the Fourier coefficients equal to 1 over 2. So the Fourier coefficients are real valued in this case. But in the Fourier series representation of sine omega 0 t, we have obtained Fourier coefficients which are pure imaginary, 1 over 2j and minus 1 over 2j. So why is this the case? So we can also discuss this case for real valued signals. Okay, so let us now see the details of this discussion. Now, in order to continue with the discussion related to the details of the Fourier series representations of real valued periodic signals, we need one more result, and it is the following. Now, suppose that we have the signal x of t with Fourier series coefficients ak. So what can we say about the Fourier series coefficients of x of minus t? Okay, x of minus t is the signal obtained from x of t by the transformation on the independent variable. That means t is replaced by minus t. So it is called the time reversal transformation. So x of t is the original signal and x of minus t is the time reversed signal. So it is quite easy to obtain the Fourier series coefficients of x of minus t as follows. Now x of t has the Fourier series representation k from minus infinity to plus infinity ak e to j k omega 0 t. So we can just substitute minus t instead of t in this expression. So we have k from minus infinity to plus infinity ak e to jk omega 0 minus t. Now again, we have instead of e to jk omega 0 t, which should be the term in the original in a Fourier series representation, we have the negative exponent. So to get rid of the negative exponent, we can change the index k to m. So let m be equal to minus k. So x of minus t is equal to a minus m e to j m omega 0 t, and m is running from plus infinity to minus infinity, but we can change the order obviously. So again, m is dummy. So change it to back to k. So x of minus t is equal to k from minus infinity to plus infinity a minus k e to j k omega 0 t. So, in this case, the Fourier series coefficients of x of minus t turns out to be a minus k. Okay. So, whenever we have a periodic signal x of t, x of minus t is also periodic, and its Fourier coefficients can be obtained from the Fourier series coefficients of the original signal x of t by means of this relation. So now we have a definition related to signals. In fact, we have two definitions. The first definition is the definition of an even signal. X of t is said to be an even signal if x of t is equal to x of minus t. So you see, in this definition of an even signal, we use the signal x of minus t. So x of t equal to x of minus t means that the signal is even, and similarly x of t is said to be odd, an odd signal, if x of t is equal to minus x of minus t. Okay. Now, after these two definitions, now we are ready to obtain some results related to real valued signals. Let x of t with the Fourier series coefficients ak be a real valued periodic signal. Now, if in addition, if x of t is even, the Fourier series coefficients AKs are real valued and the following condition is satisfied: a minus k is equal to ak. Well, it is very easy to see this because x of t is real valued. Now let us see the proof of this. X of t is real valued. So this implies that a minus k is equal to ak conjugate. And x of t is even means x of t is equal to x of minus t. Therefore, a minus k is equal to ak. But from these two expressions, it is clear that ak conjugate is equal to ak as well. which means that AK is real. So for real valued and even signals, periodic signals, the Fourier coefficients turn out to be real valued, and A minus K is equal to AK. Okay, now what happens for real valued and odd signals? Next we will see this. Okay, now very similar to our discussion related to real valued and even signals. Now x of t is real valued and odd, then the Fourier series coefficients turn out to be pure imaginary. AKs are pure imaginary, and A minus K is equal to minus AK. Now, how can we prove this result? Again, we first use the fact that x of t is real valued. This implies that A minus K is equal to AK conjugate. And x of t is odd, means x of t is equal to minus x of minus t. Therefore, A minus K will be equal to minus AK. Now, again, when you compare these two, since we have A minus K equal to AK conjugate and A minus K equal to minus AK, this means that AK conjugate is equal to minus AK, and this is only possible if AK is pure imaginary. So from here we see that AK is pure imaginary. Okay. So we have obtained several important and interesting results related to real valued signals. For real valued signals, in the Fourier series coefficients, there is a certain relationship between the Fourier series coefficients with positive index and negative index. So this means that if you have a certain positive frequency component, you necessarily have a negative frequency counterpart. And also we have obtained the conditions that should be satisfied by the Fourier series coefficients for real valued even and odd signals. Now, after this, we have one more result. In fact, it is a result completely related to the previous results, and it is the following. Again, let us consider x of t is a real valued periodic signal. So x of t has the Fourier series coefficients AK. Okay, we know that A minus k is equal to ak conjugate, obviously. But now, let us continue as follows. X of t can be written as the superposition of its even and odd parts. So we write x of t as even part of x of t plus odd part of x of t as follows. Even part of x of t is equal to x of t plus x of minus t divided by 2, and odd part of x of t is x of t minus x of minus t divided by 2. Now, x of t is periodic, therefore its even part and odd part, these two signals, are also periodic. And what can we say about the Fourier series coefficients of these two signals? So, even part of x of t will be periodic with the Fourier series coefficients, which are obtained from the original AKs by means of this operation, real part of AK. So the Fourier series coefficients of the even part of x of t will be real part of the Fourier series coefficients of the original periodic signal, and similarly the odd part of x of t will also be periodic, and its Fourier series coefficients will be j times imaginary part of ak. Okay, so that is how we obtain the Fourier series coefficients of the imaginary part and odd part of a periodic signal. Okay, so we can stop at this point. Thanks for watching.